We still continue with our chemistry class. Remember, I started on the topic structure of the atom and periodic table. We are still continuing with it. And let's look at the recap of what we learned last. Started the topic the structure of the atom and periodic table, where we say that atom is the smallest particle of an element that can take part in a chemical reaction. And we say the atom is made up of three subparticles. We have protons, electrons, and neutrons. Protons, we gave characteristics of each of the three subparticles. We say protons are positively charged. They are found in the center of an atom called nucleus. They have a relative mass of 1. And then we say that number of protons in an atom of an element is its atomic number. Then the electron, we say, is negatively charged. It is found in the fixed region surrounding the center of an atom called energy levels or orbitals. Has a relative mass of 1 over 1840. The number of protons and electrons in an atom of an element is always equal. Then for neutrons, we say they are neither positive nor negative, thus they are neutral. Like protons, they are found in the center of an atom called nucleus. They have a relative mass of 1. Number of protons and neutrons in an atom of an element, the summation is the mass number. Then we went further and drew a simple structure of an atom, where we say that this being the structure of an atom, we say that at the center we have the protons, and neutrons. Then the area surrounding the center, we have the electrons. Now, at the center here, protons and neutrons are found in the nucleus. And the nucleus is always positively charged because of the charge of protons. Now I went further and gave the first 20 elements of periodic table. And their symbols. Remember, in Form 1, we just learned but a few of the elements and their symbols. So here we shall learn for the first 20 elements. The first one being hydrogen. Second one is helium. Third, we have lithium. Fourth, we have beryllium. Fifth, we have boron. Sixth, we have carbon. Seventh, we have nitrogen. Eighth, we have oxygen. Ninth, we have fluorine. 10th, we have neon. 11, we have sodium. 12, we have magnesium. 13, we have aluminium. 14, we have silicon. 15, we have phosphorus. 16 you have sulfur, 17 you have chlorine, 18 you have argon, 19 you have potassium, then 20 you have calcium. So these are the first 20 elements of periodic table. So each element has a unique symbol that we use it while indicating in the periodic table. Like for the case of hydrogen, it has capital H, helium is He, lithium is Li, beryllium is Be, boron is B, carbon is C, nitrogen N, oxygen O, fluorine is F, neon is Ne, sodium is Na, magnesium is Mg, aluminium is Al, silicon is Si, phosphorus is P, sulfur is S, chlorine is Cl, argon is Ar, potassium is Ka, calcium is Ca. So those are the first 20 elements of periodic table with their symbols. So while drawing the structure, while drawing the periodic table, we'll be required to indicate them using the symbols. We'll indicate them using the symbol. Even when we are drawing, when we are writing the chemical formula, we'll be indicating those reactions. We'll be indicating those reactions using the symbols. So it is good that when we master them, it will be easier for us. Having looked at this, the first 20 elements and their symbols, we say that in the structure of an atom, electrons cover the region surrounding the center. The electrons cover the region surrounding the center, and they are in energy level. So electrons are in energy levels that surrounds the center, or orbitals that surrounds the center. That surround the center. Electrons in energy levels are represented by dots or crosses. So, electrons cover the region around the nucleus and they are in energy levels or orbitals. So electrons, they cover the region around the nucleus, and these electrons are in energy levels or orbitals. The electrons in energy levels, electrons in energy levels, electrons in energy levels are represented using either dot or cross. So while indicating them in the energy levels, we'll either use a dot or a cross, but we cannot use both of them. So let's have this as our atom, as the structure for our atom, having protons and neutrons in the center, first energy level, second energy level, and perhaps third energy level. So, while indicating them in these energy levels, we represent them using a dot or a cross. So, that's how we will present our electrons in a given structure of the atom. Now, electrons occupying the first energy level have lower energy compared to those in the second energy level. Like here, we name these energy levels beginning from the one nearest to the center. Now, this one becomes our first energy level, this one our second energy level, this one our third energy level. So we are saying that electrons in this first energy level have lower energy compared to those in the second energy level, and those in the second energy level have lower energy compared to those in the third energy level. So we can say that energy increase as one moves. The energy of electrons in energy levels increase as one moves far away from the center. Energy of electrons increases as one moves away from the center. Energy of electrons in energy levels increases as one moves far away from the center. Now, these energy levels carry a given number of electrons. They carry a given number of electrons. The energy levels carry a given number of electrons. They carry a given number of electrons. For the case of the first energy level, it will have a maximum number of electrons that it can carry. The second one and the third one as they continue like that. So, maximum number of electrons energy level can hold, we are saying that is the maximum number of electrons an energy level can hold is given by, we have here formula 2n squared, where n is the number of energy level. So we are giving the formula as 2n squared, where n represents the number of energy level. For example, in the first energy level, we'll have it as 2, where our n becomes 1, which will give us 2. So the maximum number of electrons the first energy level can hold is only 2. For the second one, it will be 2 squared, which will be 8. So this formula only applies for the first 2 energy levels in the first 20 elements of periodic table. For the third one, it only holds a maximum of 8. For the third one, only holds a maximum of 8. That is for the case of the first 20 elements of the periodic table. It will only hold 8 electrons for the first 20 elements of periodic table. But for the fourth one, still the formula applies. The formula does not only apply for the third energy level in the first 20 elements of periodic table. So let's go further and see electron arrangement. Electron arrangement in the first 20 elements of periodic table. Let's go further and see the electron arrangement in the first 20 elements of periodic table. So the electron arrangement in the first 20. So electron arrangement. Let's have here element. Number of protons. We have the electrons in the first energy level, electrons in the second energy level, electrons in third energy level, fourth energy level, then the electron arrangement itself or electron configuration is still the same. Yes, means it's the same. Now we start with hydrogen. Helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. Then let's do up to sodium. Then you have sodium. So let's go with the first 11. Then for the remaining 9, you'll have to practice about it to see how if you have understood. So protons in hydrogen is 1, of protons 1, helium it is 2, 3 in lithium, 4 beryllium, 5 boron, 6 carbon, 7 nitrogen, 8 oxygen, 9 fluorine, 10 neon, 11 sodium. So we said that number of protons and number of electrons are the same. And remember, electron arrangement, we use the number of electrons. Now, we say that in the first energy level, it only carries a maximum of 2. For hydrogen, it only has 1. It only has 1. But we say that we indicate the electron either using a dot or a cross. So we'll have 1 cross. Helium, it is 2 crosses. Lithium, 2 maximum. The remaining one goes to the second energy level. Beryllium, 2. Remaining 2 second energy level. Boron, we have 2. The remaining 3 second energy level. We have 2. 4 in the second energy level. We have 2. 5 in the second energy level. We have 2. 6 in the second energy level. We have 2. 7 in the second energy level. We have 2, the remaining 8 in the second energy level. For the case of sodium, we have 2 here, then 8 here, then the remaining one in the third energy level. As long as the energy level is full, the remaining one goes to the following energy level. Now, here we indicate the electron arrangement or the electron configuration. It is 1, helium is 2, lithium is 2 in the first energy level. Then we separate the energy level using a dot. 1, 2, 2, 2, 3, 2, 4, 2, 5, 2, 6, 2, 7, 2, 8, 2, 8, 1. Because the second energy level is full, we move to the third energy level. That's also what happens when when the third energy level is full, we move to the fourth energy level. Those are the electron arrangement for this first level. Now for the remaining 9, you can try and see if you have understood about them. But if you are unable to do, you can comment and we can help. Then, the arrangement of electrons in an atom helps in explaining patterns in properties of elements, and the properties at the basis for the periodic table. Now, this electron arrangement helps us in explaining the pattern. This electron arrangement helps us in explaining the pattern. And remember, the pattern in properties of electron, and remember the properties are the basis for the drawing of the periodic table or coming up with a periodic table. Now, after having known how to come up with the electron arrangement of any given element, now while drawing the structure at this moment, we indicate the electron arrangement or the electron configuration for the given atom that we are drawing. For example, when we draw the structure of fluorine, you know that fluorine, its atomic number has 9 electrons, 9 protons, because number of protons and electrons are the same. Now we do the structure beginning with the center, having protons and neutrons, the first energy level. We indicate the number with the electrons in the first energy level, say it's a maximum of 2. Then the second energy level occupies the remaining one as long as does not exceed 8. 4, 5, 6, 7. So that is fluorine. Then the symbol for fluorine is F. Now the electron configuration 2, 7. At that moment we'll have drawn the structure of fluorine, indicating the electron configuration. Now we can draw the structure of any given, the atomic structure of any given element, having known that. Then having said that, let's move to characteristics, atomic characteristics. Atomic characteristics. Atomic characteristics. We start. The first one is atomic number. Atomic number. Now, atomic number tells us how many protons are there in a nucleus, and it is denoted by capital Z. Tells us how many protons are there in nucleus, and is denoted by capital Z. So the atomic number is denoted by capital Z. Atomic number equals the number of protons and also equal to the number of electrons. The atomic number equals to number of protons and also number of electrons. So the number of electrons, number of protons, and atomic number are the same in any given element. They are the same. The second one is mass number. 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 Mass number is the sum of protons and neutrons in nucleus. Mass number is the sum of protons and neutrons in nucleus. Now the summation of the protons and the protons and neutrons. Therefore, it is always bigger than the atomic number and is denoted by capital A. Denoted by capital A. To get the number of neutrons, we just subtract the atomic number from the mass number. Now, we say that the mass number is the summation of protons and neutrons in nucleus is denoted by A. Now, when you want to get the number of neutrons, we'll just subtract the atomic number from mass number. Just subtract atomic number from mass number. We'll have the number of neutrons. Let's look at an example of calculating the number of neutrons. Calculate number of neutrons in a chlorine atom. Calculate number of neutrons in a chlorine atom given that the atomic number Z equals to 17 and mass number A equals to 35. Now we say that for us to get neutrons, we subtract atomic number from the mass number. Mass number is A, atomic number is Z. So you take 35, 17. I'll have it as 18. The number of protons becomes 18. Therefore, chlorine atom has 18 neutrons. Remember that since the number of protons and electrons are equal in an atom, once atomic number is known, it's just the same as the number of protons and the number of electrons. So when you are required to do the atomic structure of an atom, showing the subparticles, the subatomic particles, it is easier. Once you are given the mass number and the atomic number, it is easier to go about it. Let's look at example when we required to calculate the number of neutrons. Then further you are required again to draw the structure of the given element. Now this example B, a certain element X has atomic number a certain element X has atomic number 6 and mass number 14. A certain element X has atomic number 6 and mass number 14. Draw the atomic structure of element X. Draw the atomic structure of element X, showing all the subatomic particles. Now we are told that a certain element X has atomic number 6, and mass number 14. Then we are told to draw the atomic structure showing all the subatomic particles. Showing all the subatomic particles. So he said that when we know the atomic number and the mass number, we can go further to calculate the number of neutrons. Now we have mass number, say it's 14, atomic number 6. Now to come up with number of protons, of neutrons, we subtract atomic number from mass number. 14 to have it as 8. Now we know that the number of protons, number of protons and electrons are the same as the atomic number. Now we draw a structure having known the number of neutrons, number of electrons, and number of protons. We start with the center, having 6 protons, 8 neutrons, and then the first energy level. We indicate the number of electrons, 1, 2. Second energy level, we'll have the remaining 1, 2, 3, and then 4. That one becomes our structure. Then we indicate, because we say this element X, electron configuration is 2, 4. That's our element already drawn with all the subatomic particles in it. So at that we can draw any structure of given element with all ease, because you have known all that is required. Because you have known all that is required for us to draw any structure of an atom. So we usually write the symbol of an atom, the symbol of an element, the symbol of an element, including the mass number and the atomic number, because in the periodic table, that's how you'll find them. Find the symbol drawn bearing mass number and the atomic number. Now, the atomic number is Z, and the mass number is indicated using A. Of an atom, of an element, X can be written alongside the symbol of the element as a subscript, as a superscript, and others as a subscript. Now, we have the symbol being X. We have our mass number A. Now, our mass number being A becomes our superscript A. Then the atomic number becomes our subscript. That's how we'll be writing the symbol of an element with mass number and the atomic number. Mass number being a superscript and the atomic number being a subscript. For example, when we are given sodium, the symbol is Na. The atomic number is 11. Mass number is 23. Mass number is 23. Now this is the symbol of sodium, having the mass number and the atomic number. Now the one on top, we are saying it is mass number. It is the superscript, and then on the bottom it's subscript, which is the atomic number. We can also represent subatomic particles using symbol with mass of the particle as superscript and charge as a subscript. We can also draw the subatomic particles. We have protons, we have electrons, then we have neutrons. We can also write them having the mass and the charge as the subscript. For case of proton, you have P. It has a mass of 1 and a charge of positive, that is 1. Electrons, we have small e. It has a mass of 1 over 1840. So we negate it to be 0. It has a negative charge, that is negative 1. Then for the case of neutron has a mass of 1 and it is neutron. So that's how we can get the subparticle elements having the mass and the charge. Let's look at our last part for today, which is isotopes. Now we are all familiar with the charcoal. Which is black in color, and in chemistry, charcoal is just carbon. A piece of charcoal is made up of millions of carbon atoms. Carbon exists in two forms represented as carbon 12 and carbon 14. Now, they are saying that charcoal has a million of carbon atoms. And charcoal is represented using two forms of carbon. We have carbon 12 being the mass number, 6 being the atomic number, then carbon 14 as the number. So we can see the difference, and we can also represent them. We can also draw their structures. To see the difference, where the difference is. So we can tell that the difference is in mass number. This one has 12. This one has 14. What does it mean? Because mass number is summation of protons and neutrons. Now it means that there is a difference in mass number. Because protons are the same, which is 6 atomic number, which is same as the number of electrons and number of protons. Now the difference comes in the number of neutrons. The difference is seen in the number of neutrons This means that they have the same atomic number but different mass number. Same atomic number but different mass number. Isotopes. Now let's define isotopes. Are atoms of the same element which have same atomic number but different mass number. Isotopes are atoms of the same element. Isotopes are atoms of the same element. Atoms of same element with same atomic number but different mass number. But different mass number. Or you can say same number of protons but different number of neutrons. Now you have different elements having isotopes. Different elements having isotopes. So isotopes are atoms of the same element with same atomic number but different mass number, or same number of protons but different number of neutrons. Different number of neutrons. Now, the isotopes has only a different mass number or the number of electrons.